Hello and welcome to the next episode of the Klingberg Wing Mark II development. I'm Raul Klingberg, your host. Today we're out in the chilly garage. Well, it's not really cold winter yet, but it's starting to get chilly here, so that I can show you the spars for the main wing panels. The main wing panels run from the center section, which is 30 inches wide, out to the wing tips. They're about 18.5 feet long, so you're not going to see the whole thing in the beginning part of this video. But we're looking at the root end of the left spar here, and in the back here I have the tip end of the right spar. The spars are done, and as you can see they have carbon fiber shear webs. That's on both sides. Out at the tips they're fiberglass, and this carbon fiber I've used a molding process to form flanges on the edges, top and bottom, and that's so that the top of the spar has about 1.5 inches of width to allow for bonding of the D-tube and either rib cap strips or aft composite sheeting for the wing. It's a traditional I-beam construction. It has a pretty much standard wood and foam core, and the materials, composite materials, are formed on the outside. The number of layers and how they're laid up are in the following video, which is very long, so I'm going to try to keep this part short. And as a last piece, it has some fiberglass across the top here, a little bit of filling on the core to make sure it's level, and then fiberglass, and I explain in the video why this fiberglass is across the top of those flanges. And what you see here is I've done a dry fit of the root fittings here. These are the fittings that the big pin drops in to attach the wing panels to the center section. And I'll be bonding these on probably this weekend. I'll get this done. I've been really happy. This process has gone a lot quicker than I thought it would. It really only took a couple of weeks, maybe 3 weeks total, to glue up the cores and do the layups, and the spars are done. I was surprised at how smoothly it went and the limited number of hours required to do it. The root fittings here are not bonded on yet. After they're bonded on, they'll get bonded right to the shear web here, and that's where the cap strips are also. You'll see that in the video. And then after that bonding is cured, I have these 1/4 inch wide pole-truded carbon fiber strips, which are going to come in here much like I did the spar carry through in the center section. They're going to bond on here and wrap around this fitting and down the other side, and this carries the loads out along the spar cap and provides more bonding area. There's a total of 4 of these. 2 of them stacked like this on the fitting. These are 1/4 inch, 1/2 inch fittings, so we get 2 of them on here, and then 2 layers thick. Now these are not designed to carry the entire load. Most of the load is carried in the fitting itself. You can see it's a 1/2 inch thick. It's about a 1/2 inch wide here. Really strong fitting. But this provides more bonding area and helps carry some of the tension loads. At an absolute load of 9 Gs, there's about 30,000 pounds of tension load or compression load in these fittings. So a little extra belt and suspenders doesn't hurt. These little strips don't weigh much, and they will greatly increase the bond area and help carry a lot of load. So, good thing. Get ready to do that this weekend. On the right spar here, I can show you the fittings for the wingtips are already in place. They've been bonded on here. They're done in a highly similar fashion. They slip over the shear web and grip the spar caps that are down here. But these will have 2 small stainless steel bolts go through here and tighten down lightly, and those bolts are to carry any peeling loads that are trying to pull this fitting apart and take it off of the spar. This will have a carbon fiber pin. This is a solid rod of carbon fiber, and it'll slide through here, and that'll be the attachment pin for putting the wingtips on. So we have a long video coming. I hope you have a chance to watch the whole thing, maybe watch it in segments. I think it's probably up around getting close to an hour by now, but it's full of great information that if you're a builder, I think you'll find useful. So come on along, enjoy the video, and I'll see you again at the end as we close out. Now, before I begin the layup of the face sheets for the spars, I thought I'd take you on a little tour of the shear web and how it's constructed. Excuse me while I walk to the other end here. This is the root end of the shear web. This is where it attaches to the center section of the wing. There's a couple of fittings that'll go on here. You see it looks essentially the same on both sides. Predominantly, the most important thing is the spar caps right here. There are two strips of 1 millimeter by 10 millimeter pultruded carbon fiber, good to about 300,000 psi, which is very, very strong. There's 4 of those on each edge. There's 2 on this side, 2 on the other side, and of course we got them top and bottom. And that carries the vast majority of the tension and compression loads. In fact, the calculations for the spar strength are based on these spar caps only. Of course, the shear webs themselves, the D-tube skin, various other factors of the design also carry some of the bending loads, but those I consider to be margin. To take compressive loads here right at the root, I have basswood in here. Basswood runs about 20 pounds per cubic foot. A couple pieces of it tapering out here to take any of the bending loads. We don't want any stress risers by having a square corner. These actually taper all the way to a point out here underneath the spar caps. And the fittings that slip on here for attachments slip on right over the top of these spar caps and get bonded in place, and load straps are put on those. The core material right here in the area of the wood is 6 pound per excuse me. The core material here at the root end near the wood is 6 pound per cubic foot urethane foam. It has very high compressive strength for foam, and it's appropriate for putting up against the wood and carrying the loads that are here at the root. And that material ends right here at the seam, and it looks like it continues here, but this is actually Divinycell foam. Actually, this is Airex foam. This is Airex foam that runs about 3 pounds per cubic foot, and it's actually a face sheet on the top of the blue Dow styrofoam that comprises most of the spar. You can see right here where that urethane foam ends and the blue foam takes over. The reason that we have some Airex foam on this side is to make up the thickness differential. The Dow blue styrofoam was slightly under a ½ inch thick. This wood is a ½ inch thick. This foam is a ½ inch thick. And the blue foam was just a little under that, so the Airex foam here makes up the thickness differences. Now you'll note that the spar caps are bonded right on to the foam core, so there's a 1 millimeter step here which I've filled in with lightweight microballoon filler, available at most hardware stores, home improvement stores, hobby supply. I do not recommend the DAP product. They recently changed the adhesive that they use, and it just does not sand well. So look online. I'll provide a link here in the video to the product that I use. The spar caps themselves are bonded on with T88 structural adhesive that's way in excess of the strength of the foam. I could have used a 15-minute cure epoxy, or actually probably 30-minute, because it takes a while to spread out all the epoxy and put the spar caps on. And I'll run a couple photos here as I discuss the spar, showing installation of these cap strips and how that was done. We might take a short segment, a few photos, and I'll step you through that process. So the Airex doubler runs out here, and now you see the blue Dow styrofoam reappear again, and the microballoon filler here providing a ramp between the two. This Airex foam is about 3/32 of an inch thick, give or take. It might only be a 1/16, something like that. And the filler continues along here, along the spar caps, and that filler provides a ramp for the carbon fiber face sheets that I'm going to put on here. We don't want to have a square corner here. A lot of people would think that the epoxy resin is going to fill that corner, but you'll get a lot of voids, and that greatly reduces the strength. So we have to provide some type of surface for the foam, for the carbon fiber to ride on, and for the epoxy to glue to. And the correct filler is any filler that's about the same density as the foam itself. Here at the root end, where I have the wood, in the upcoming video here, you'll see me actually mix up some microballoons and 5-minute epoxy and put that right in this area, because we want something that's a little higher density and a little stronger to support the cloth in the area of the wood. We want something that's comparable to the density of the wood. So let's walk back down here to the other end towards the tip, and we'll talk a little bit about the blue Dow styrofoam that comprises most of the shear web. I'll give you a shot here along the length of it, and you'll see upside down here, this is actually the left wing that I'm working on and about to put the first face sheet on it. The blue Dow styrofoam also comes in pink. I believe that the blue and pink have the same mechanical properties, and this is cut from 2-inch thick sheets into half-inch thick sheets. Buy it that way from Aircraft Spruce and Specialty. I really like the blue Dow styrofoam for these types of projects. It has a 2 pound per cubic foot density, which is better than any of the Airex foams or any of the other PVC-based foams that are out there. Its drawback is that it's polystyrene, and it doesn't have quite the same compressive strength as an Airex foam or a PVC foam, and it is susceptible to solvents. The PVC foams are resistant to most solvents that you would use to clean the cap strips before you bond to them, but the polystyrene is susceptible to most solvents except for alcohol. And therefore, when I clean these cap strips prior to laying up the face sheets, I'll be using alcohol to clean them so that I don't damage this foam. If we damage this foam, the entire spar would be lost at this point, and that would be a big dollar and labor loss, so we don't want to make that boo-boo. Now, you're going to see along the side here, there's some angle stock here, and it has some white fabric attached to it. And I have a straight edge here along this side attached to the bench, screwed in place. That runs the whole length. This is just a series of aluminum L brackets, and you can use a laser to align them. I just used a tight string and made an absolutely straight edge here for molding the spar itself, keeping the spar straight. And the table provides a level surface to make sure that we're both straight and flat. These brackets here, this L bracket and these brackets, when brought up tight to the spar, we're going to push the spar tight together here. I will be putting clamps on here across this way to hold the spar tightly in place, and then when the carbon fiber goes in place here, it will actually form the little lip right here that we need for attachment of the D-tube and the rear skins. And I'll take you over to the first spar that I did here. Here's the right wing, and you'll see here that we have a flange that is formed. So I'm forming the face sheet here and the flanges for the D-tube attachment simultaneously. It's all done in one layup. It's really pretty straightforward and pretty easy to do. The white fabric that you see here on the other forming bracket, this just happens to be a square piece of tubing because I already had that in stock. This is peel ply, and this provides a surface where the epoxy does not stick and provides a rough finish on the final product so that we can do secondary bonding of the D-tube and other components. That is absolutely critical. You don't want to have a smooth surface there at all. Don't think that you're going to have a smooth surface and then just be able to sand it down a little. These flanges, as you can hear, are very thin. They're only one layer thick. You can't really do any sanding on those. And you want to make absolutely certain that you have the proper surface finish, and that's done with peel ply. This is 2-inch wide Dacron, available from Aircraft Spruce. There's also a Teflon version. Let me see if I can grab some of it here. You can get this material is also a peel ply. This is fiberglass with Teflon on it, extremely slippery, nothing ever sticks to it, real easy to remove and work with, expensive though. This is about twice the cost of working with Dacron peel ply. I'm using the Dacron peel ply because it's low cost, easy to use, flexible, a little harder to remove, but that's okay, we just do a little bit of extra work. Now I have that cloth attached to the forming bracket here with some double-faced tape, and the brackets themselves, the square tube and the other L brackets, have tape on them. Same's true on this side. This bracket that the spar is up against here, let me move it away a little bit. You'll see on this one, I have the peel ply fabric on here also, and I have it actually going down around the corner so we don't have any sticking in the corner here should excess epoxy run down there. And this is attached to this bracket with double-faced tape also. So how this works for the layup is the spar gets pushed up against that one former. this former comes in place on this side. As I said, I put a clamp across this way to hold it tight together. And then I come in with these 1x2s. This is a 1x2 that has packing tape put on it so the epoxy doesn't stick. And it's going to go in the corner here. We're going to have one on this side. There'll be one on this side over here. And these get clamped in place both this way, so it's tight to the bracket, and it gets weight put on top to hold it down tight. So the weight on top holds the whole assembly flat to the table, and the clamp here and over here, I can't show the other 1x2 right now, it's under the carbon fiber cloth. So if for the one that's over here, this will be clamped this way, and this one gets clamped over here this way. And then we have clamp set right over the top of the whole thing. And I'll run up a photo here that you can see that clamping arrangement for the entire spar. I did round off this corner here that goes in on the inside corner here. That has about a 1/32, 16th inch radius on it. We don't want to actually kink the cloth in the corner. We would not want a square 90-degree corner on that cloth because that would kink the fibers and weaken them. So just a small radius here before I applied the tape. And that's the basic setup. No vacuum bagging required. I just used some concrete blocks for pressure on top. You'll see that in the photo also. And the whole layup takes about an hour, hour and a half. Have to work in chunks to get it done. Now the layup for this side of the shear web, I'm going to be laying up, in the video that's coming here, I'll be laying up this face sheet, which is the inside of the D-tube. So the inside of the D-tube is designed to be a little bit stronger than the aft side. The aft side is exposed to or attached to the aft wing skins, which could be, the aft wing skins are composite, and some of them are fabric. So the aft face of the spar does not need to be as strong as the forward face. We want the forward face as strong as the D-tube itself because that literally makes the tube. That's the back wall of the D-tube. And we want to have good torsional strength on the D-tube, and that's done with the carbon fiber cloth on the face here. So what we have here for this layup, we have one layer of carbon fiber here at the root. This is 6-ounce cloth. This is cut straight. There's no bias on this. And the edges will get cut off here so that this cloth will run it'll butt up against here and it will butt up against the other side. So this doubler will just run across these cap strips here like this and end right at this edge. It does not get folded up around the corner. And that only runs out till it's a little past the joint here on the foam. And then we have the carbon fiber laid up on the bias, 45-degree bias. This is 6-ounce cloth, runs out here for out to here, and then we run out to here, and we run out to here, and it's one layer. So here at the root, we have 2 layers, and out here we have 1 layer of 6-ounce cloth. And this actually does get molded up around these brackets. And when it's 90% cured, I come along with a razor blade, and I'll cut it off at the top of these brackets here, and that sets the width of this flange. The width of this flange is set by trimming it before it's fully cured right to the edge of the molding brackets. Okay, so the last thing that I should point out to you, let's see, what else do you need to know? Oh, you probably want to know out here. Out at the tip where the loads are lower, I'm using the spread toe carbon fiber to save some weight. This is 2.65 ounce cloth, so I just call it 3 ounce. So it's about half the weight of this cloth, and it's also laid up on the bias, which you can readily see here. It's always very pretty cloth, but we're not using it for its looks. We're using it for its mechanical properties. It's lighter weight, very strong, and you can see it molds up very nicely here on the tip. This is a little bit more difficult to work with. In the video coming, you'll see me struggle a little bit to wet this out. I'm going to wet out this surface first and then put more epoxy on the outside of this, and I have to work a little extra hard to work the epoxy into it because it is such a tight weave. It's a little more difficult to get the resin through it than normal woven cloth. Now all of this is laid up on the bias, of course. If you're familiar with this type of construction, you want the fibers running this way, and they're when the shear loads are applied, that puts these fibers more in tension, which is what we want because carbon fiber performs best in tension. In addition, by laying it up on the bias, we're able to take some of the bending loads also. As the shear forces are applied here opposite of each other, you got a load going this way, and here you have a load going this way, you get the bending loads. It puts these fibers in tension, and these fibers can actually contribute significantly to the resisting the bending loads. Same is true of the spread toe. It's probably even better at it. Nice wide flat fibers there aligned with the loads that are applied. It's not included in the calculations of the strength of the wing, and if I needed to reduce the weight of the aircraft, I could include that in the calculations and probably reduce the size of the spar caps. But that's not critical for this prototype aircraft. So there you go. That's the whole layup. When these sections are put together, there's about a 2-inch overlap. That's pretty common practice. It's acknowledged that a 2-inch overlap is sufficient to consider this as one piece of cloth instead of separate sections. So there we go, and we're going to switch over to a fast forward here so you can watch me do this layup. Wish me luck that it goes well. I don't want to lose the entire spar, and here we go.
Like a bird on a tree, I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit together. It's so beautiful, you and me. We meant to be in the great outdoors, forever free. Sometimes you need to go and take a step back to see the truth around you. From a distance you can tell. You and me were meant to be in the great outdoors,
thought we'd take a few moments here to discuss installation or application of the face sheet to the other side of the shear web. The front side has been done. The front side is what faces towards the leading edge, and the flange, it's been put on, and the flange has been formed here, and we're looking here at the back side, and you can still see the basswood cores that are here. This is the 6-pound urethane foam, and on the back side it is just the blue foam. There is no doubler here of the PVC or aerosol foam. I forgot to mention earlier, one of the key things I like about the extruded polystyrene foam, it might have some other drawbacks, but its big plus is extremely tight cell structure, and the cells are closed. So very little epoxy actually goes into the foam when you do the layup. You may note on most of my layups, I wet out the fabric prior to applying it to the foam, and that is because of that open cell structure on the foam. I'm using the excess resin that's in the fabric to bond to the foam. If you were to put the fabric on the foam first and then wet it out, all of those cells fill up with resin. And I'll give you the kind of difference it makes. You may remember on the front side of this, there's a stretch here of from about here to here, actually runs further out, of the PVC foam, which has a much more open cell structure on it. And on one of the spars, I left that open. On the other spar, I filled it in with microballoon filler, the lightweight microballoon filler that's used for models. And the difference was about 2 ounces in the weight of the spar. So out of a 9-pound, little under 9-pound spar, 2 ounces was just in resin going into the fill up those cells that provides no strength whatsoever. Coming in with microballoons, lightweight filler, saves those 2 ounces, a little bit more work, makes all the difference. However, the blue foam, don't need to fill it at all, can just put the dry fabric right on here and wet it out. You'll notice in the video that you've been watching that I wet out the spar caps first to make sure that they are completely wetted out and in full contact with the fabric. We don't want any dry spots on the spar caps, and then I go ahead and wet out the middle section. Sometimes I just brush a little bit on the foam before I put the fabric on, help hold it in place. So blue foam, very good in terms of not sucking up too much resin. Now let me show you how I'm going to do this. The front side's already been done, and what I've done here is I've taken 1/2-inch thick 1-pound beadboard foam and cut pieces to fit in between the two flanges, and that is for the spar to sit on the table like this, and that protects the flanges from getting damaged when I put the weights on top. I bought that foam commercially cut 1/2-inch thick, usually available at Home Depot, and that ensures that the whole spar is still sitting level. We won't want to have any variances along the length in terms of that support, or we'd end up with a crooked spar. And you'll see here, if I run it up against my fence here, you'll note that it is, because of that foam, it's now taller than the fence. So I don't have a fence to form the flange on. So what I'm doing is I have taken a 1x2 right here. You can see it here. And I've applied some, if I can get you around here, some foam core board to the 1x2, making it a little bit taller this way. The whole thing's wrapped in plastic tape so nothing sticks. And on this side, I've applied some peel ply fabric, 2-inch wide peel ply, and it's held onto the 1x2 with some double face tape. And that 1x2 goes right up against the fence like this. You can see the 1x2 up against the fence. The fabric wraps down around inside, and then when the spar comes in here like this, when I set this in here, there we go. And now this 1x2 sticks up above the spar and provides the surface for molding the flange. And because I put the peel ply on the 1x2, when that flange wraps up and around like this, we'll have the peel ply release surface. And I'm going to do the same thing on the other side over here. And then same process that you just watched. Going to come in with, sorry about this, trying to do this and hold the camera at the same time. Well, I'll come in with another 1x2 like this. You'll see it in the time-lapse fast forward. and clamp this to hold that flange shape while the epoxy cures. Essentially the same process that we used on the first side. So let me put that back and let me walk you through what we're putting on here. We're putting on one layer of 6-ounce basket weave or plain weave carbon fiber cloth cut on the bias. You can see that angle cut here. That's going to run from the root end out to about here. And then we have the spread toe carbon fiber, 2.9 ounce, something like that. We'll call it 3 ounce. And we have that goes for 2 pitches here. It goes out quite a ways, very close to the tip. And then out at the tip we have some 3 ounce fiberglass. It's the 120 style satin weave. This is not laid up on the bias. The way that it's woven doesn't make too much difference the way you lay it out. This will still be appropriate, just a cutter square, and it'll still be good for the shear web. Now you might be wondering, gee, Raul, that's a completely different layup than you used on the front side. And that is true, because the entire front side of the spar is the back closure, the rear closure of the D-tube. And it is what actually forms the tube and gives the whole spar its torsional rigidity. So the front side of the spar is critical to the torsional rigidity of the wing and also to the shear strength. The back side, well, at the root end, as you may remember or note, that the center of the wing, the flat portion, has composite skins on it. Those composite skins will be glued to these flanges that are going to be right here and to a rear spar. So the section of the wing that encompasses the flaps is a full tube, composite tube structure. It has composite skins and it has a composite face here at the front, and then the rear spar is composite. So that is another tubular section, very large, that helps carry torsional loads. So therefore, that portion of the wing has the carbon fiber, the stronger carbon fiber, and I'm reducing the weight of the fabric and type of fabric as I go out along the spar because the loads are going down. But out here at the tip, we're into the flap section, or excuse me, we're into the elevon section, and that portion of the wing has fabric covering on the aft portion, and it's just not necessary or needed to have a very high strength shear web on this side. The front side of the spar is taking all the shear loads, most of the shear loads, and we can lighten up and use less expensive fabric on the back side and save a little weight. In fact, it saves about 8 ounces. The difference between the front side of the spar and the back side of the spar is about 8 ounces in weight of fabric and epoxy. So it's well worth to go to the trouble to tailor this to the loads that are being applied. That's one of the secrets of this entire aircraft to keep the weight down, is all the components highly tailored to just the loads that are there. That means it's harder to build, more complicated, but it's really critical to saving the weight. So I'm going to set you up here, and we're going to do a little time lapse, and you're going to watch me do the layup on the back side, and I hope you enjoy watching that. Bye for now. and welcome back. Thanks for watching that video of layup of the backside of the main spar. And I thought I would just demonstrate to you here a little bit how I'm going to finish up the spar caps, the flanges that attach to the D-tube. What you'll see here is that I've masked off the flanges from the core material here, and this shows it a little bit better. We see the blue foam core here, and the actual spar caps themselves are on either side, and then we have the flanges for attaching the D-tube and the aft skin and rib cap strips. So in any molding process like this that's not highly accurate, there'll be low spots and high spots. So there are some spots along here where the foam is a little bit lower than the flanges, and we need to fill that space in. And that's what I'm getting set up to do here. The tape will prevent me from prematurely getting epoxy and microballoon filler on the flanges. I'm going to fill any low spots here with a mix of laminating resin and microballoons. And I'm especially concerned about, because we wanted to round off the flanges, the face sheet here has got a little round in the corner. You remember that's how I did the wood. It leaves a little gap here, and you can see that is a dark line here. And I'm going to fill that gap. I'll carefully mask this off so that that gap is still exposed, and then I'm going to come in just with my little tongue depressor stick and spread epoxy and microballoons in there and level this all out. And then once I have that filled, I will remove the tape from these flanges like this. So the center part will be filled and the tape's off like this. And then I'll come back and I'll apply a light coat of resin to the flanges themselves. And then I'm going to come in with this handy dandy 1.5 inch wide fiberglass tape. And if I can do this with one hand here while I hold the camera with the other, get that guy balanced up there. Fortunately, I have some handy 1.5 inch wide fiberglass cloth, which happens to be the width of the flanges and the core material. So I don't need to trim the width at all. This fabric is about 1.5 or 2 ounce fiberglass, and that's all that's needed for this job. And what this does is the important part of this this fiberglass cap that I'm going to put on here is it transfers loads fore and aft. The D-tube will be attached to this flange here, and the aft skins to this flange back here, and they'll meet in the middle of the core material. And because they're not done as one piece, we have to get the loads from the D-tube to the aft skins and vice versa. In other words, we need to join them up and make them as one piece. And that's what this piece of cloth does. Because of the fibers that run, it's a basket weave, plain weave, so there are fibers that run lengthwise and there are fibers that run fore and aft. And it's the fibers that run this way in the cloth, fore and aft, that will transfer the loads from the D-tube to the aft skins and vice versa. So once I get it leveled off, I put that cloth in place. I'll put peel ply on top of this so that we have the right surface for bonding to later. And essentially, this is closing off the I-beam spar and making sure that it's a whole integral piece. We wouldn't want to come in and bond a skin on here and go halfway on the core and then come from the aft, go halfway on the core, because these flanges, as you put a load, let's see if I can get this in the picture, as you put a load this way, we could just peel the flange right off the core, and we don't want that. So we need one integral piece, and the fiberglass cloth on the top will do that. I'm not going to show you a video of that layup. I think it's pretty clear how you would do that. You're going to just fill this in, wet it out, put peel ply on it. When it's cured, we peel the peel ply off, and it's ready to go because the cloth is already the width that we want. Nice and simple. Once I get this cloth put in place, there's 4 pieces of this, top and bottom of the 2 spars, then the spars are done. And we're ready to move on to making the D-tubes and getting those installed on the spar, which will be very exciting. I hope you've enjoyed the videos, and I hope you come back and watch more. And in the meantime, fly safe. See you later. Bye for now.